Alright, so this is lecture 34 on deformation theorem and conservative vector fields. I was just reading Green's theorem for an annulus. It says, so suppose the boundary of the region is a pair of simple closed, and this should not be here, this is a typo, simple closed oriented curves which bound the connected region R, a subset of R2. And so here the boundary of R is given by an inner curve and an outer curve, where the inner curve is clockwise oriented and the outer curve is counterclockwise oriented. I think it would really help to have a picture here. Let me do that. So this is the region, something like this. It's got a hole in it, all right, possibly hole. So like the C out is counterclockwise oriented, all right, so this would be C out, whereas C in is clockwise oriented. All right, so clockwise oriented, it like follows the ordinary motion of a clock, like this, down there, up here, whereas counterclockwise oriented goes the opposite way, right? And the region that we're talking about is between those two, right? So R is like in here. All right. So this is a convention that if you talk about a region R and the boundary of R, the positively induced boundary is given by the counterclockwise oriented exterior boundary unioned with the clockwise oriented interior boundary. And the reason for this convention is so that we can write Green's theorem using the same notation as we did before in the case that R was simply connected. Like if R is simply connected, basically the inner curve is just it's not a curve. It's just empty, if you will. It's gone. All right. So in the case that there's no hole in the middle, you know, then this theorem and for an annulus reduces back to what we proved last time. And it turns out that you can prove Green's theorem for an annulus like this by just, all you do is you take the annulus and you cut it into two pieces, right? If you took this and you like cut it here, and here, then this part and that part would separately be, they would have no hole, right? So those would be simply connected. You can apply Green's theorem to each piece separately, and when you study the way the crosscuts appear, then like the counterclockwise oriented one from the above and the below, counterclockwise oriented from the below versus the above, they're going to be oppositely oriented at the crosscuts, and so it leads to this relation. I have a somewhat careful proof of that on the next page, but it's quite awful to look at. But that's all this proof really says, is that if you take a simply connected region like this and you label all the curves, and you've got this, you know, clockwise oriented inner curve, then you can build, you know, I'll draw the two regions, one blue for a second here. And I should find some more. So this blue region is simply connected, right? And this red region over here is also simply connected. And when you look at their counterclockwise oriented boundaries, they cancel on these crosscuts. And then the counterclockwise oriented outer, blue region and red region, when you add those boundaries together, you get an overall counterclockwise outer region. And then you through this work down here, are able to show that the inner region is in fact, well, if you can already see it, right, it's clockwise oriented. It's kind of funny. Counterclockwise for the blue and the red leads to clockwise with respect to, if you put these two together. It's not, well, anyway. These are the details. It's not anything really that complicated. It's just the tedious business of labeling everything and explaining why things cancel out. But I hope I told you enough, because I really wanted to focus more on examples this lecture. So anyway, Another way we could write it is we could recast the theorem as follows. We could say that the line integral around the outer curve of p dx plus q dy minus the well, you could I have minus the minus, but I mean the natural thing would be, before I wrote, fine, let me just say this. I would say, I mean this is more natural. I would say C out. Here's what I would write directly: p dx plus q dy plus the integral along Cn of p dx plus q dy, right? So that, what I wrote in messy, sketchy handwriting there, that is literally the integral of p dx plus q dy over the boundary of R. Remember, boundary of R is C out union Cn, where again the inner loop is clockwise oriented, whereas the outer loop is counterclockwise oriented. And you're like, well, okay, that's great, but what does it matter? I mean, why did you switch this to minus a minus, right? We can do that. The reason I did that is so now minus Cn is also counterclockwise oriented, right? Check that out. Cn clockwise implies the reversal of Cn is counterclockwise. So, and then I just gave them new names. I said C1, in fact, if C1 and C2, you can think about C1 being the outer boundary and C2 being the inner boundary, both counterclockwise oriented, then the difference of the line integrals of those two is equal to the integral over the annulus of this difference of derivatives. And furthermore, now we finally get to the deformation theorem. If, in addition, you knew that this quantity right here was 0, right, then it would give you that that integral is equal to that integral, and that is exactly what happens if partial q partial x is equal to partial p partial y. Then that integral is 0, and we get this wonderful result, which is that the line integral along C1 is equal to the line integral around C2. And let me just draw yet another picture in here. So what's going on here, the way to look at C1 and C2, all right, so we've got some region with a hole, and C1 is the outer curve, and C2 is the inner curve in my discussion. And the thing is, they're both counterclockwise oriented. All right, both counterclockwise oriented. All right. And the thing is, in between these two, this region, the region which is bounded by C1 and C2, if in that region the partial p partial y is equal to partial q partial x, then that double integral vanishes, and we just get equality of these two line integrals, which is this result is again known as the deformation theorem, because it allows us to deform the integral around C2 to the integral around C1. And maybe C2 is like a simple thing to calculate, whereas C1 is something kind of hideous to directly calculate. This is a very, very useful calculational result. So here's a statement of the theorem that I just described. And essentially the point is that if the curl of f is non-zero, then you're in trouble, right? Because remember, the p partial, that term right here is exactly the z component of the curl. So anyway, and then this region, this result equally well extends to a region with lots of holes. If you got a bunch of holes, then you can just clockwise orient every inner boundary and counterclockwise orient the outer boundary, and you get the same result. All right. And so so here's an example. I'll try to get my cover sheet here. Finally, you've been talking about Green's theorem for like 40 minutes. You haven't given me an example yet. I'm like, I know, I'm sorry. But not so sorry, I'm not going to post this. Sorry. use Green's theorem to calculate the integral around the curve, where it's the counterclockwise boundary of the rectangle 0, 1, 0, 1. So that means that we're looking at this region, right? And counterclockwise, so it's like this, then like that, then like this, then like that. And so we to do the integral directly, this is R. To do that integral directly, you'd have to parameterize those 4 separate line segments and calculate the line integral for each separately, right? That would be a pain. In this case, p is x cubed and q is xy. So apply Green's theorem, and it looks like I'm going to use the curl form of Green's theorem. In other words, the standard one. The curl one is the standard Green's theorem. When people are talking about Green's theorem, pretty much they're talking about the curl form, all right? So, and again, just to state the theorem again, it's the integral of p dx plus q dy over the boundary of the region is equal to the double integral over the region of partial q partial x minus partial p partial y dA. So the area integral oftentimes is easier to calculate, especially in this one it is. So q is yx, p is x cubed, so partial q partial x is y, and partial p partial y is 0. So I just get the integral of y dx dy from 0 to 1, 0 to 1, and that works out the, y works out to a half, because the integral of y to y is 1/2 y squared, and so we get a half. Now that is like so much easier than actually doing 4 separate line integrals or along each leg of that rectangle. I mean the square, right? And then there's another common trick I should mention. You can use Green's theorem to convert an area calculation to a line integral. Like you can go the other way around. This one, the first example, we used Green's theorem to trade a annoying line integral for a much easier area integral. But the tables can turn. You can go the other way around. In particular, this is a nice trick. If you look at the vector field 0x or minus y0, or even this one, minus y over 2, x over 2, all of these have the property that partial q partial x minus partial p partial y is 1, which means that the integral of these vector fields on the boundary of some region is going to give you the area of the region. So we can calculate the area of the region R by calculating the integral, or this integral, or that integral around the boundary. So here's an example of that. If you want to find the area of the ellipse, bounded by, x squared over a squared plus y squared b squared equal to 1, you could parameterize that by a cos t, b sine t. So dx is that, dy is that, and so we can calculate the area by doing this little trick here using Green's theorem. And x dy minus y dx is exactly ab cosine squared plus sine squared, which is just ab. So we integrate, and there's a half from up here. And so what's the integral of ab dt? Well, that's just 2 pi ab. The half cancels with 2, and we get pi ab is the area of an ellipse, which is pretty neat. Of course, if a is equal to b, we got a circle. We get pi r squared. There's also trick formulas you can do. If you integrate along a line segment, you can integrate along a line segment from x1 to y1, x2 to y2. You can get this formula, which means that you can calculate the area of a polygon with vertices like so by integrating along the corresponding line segments that connect the polygon, right? So like this line integral, what I'm trying to say here is if the points are like this, then those points bound some some regular, well, it doesn't have to be regular, but some many-sided shape in the plane, the polygon. And if we think about that as being R, then the boundary of R, counterclockwise oriented, right? It's the union of line segments, right? Line segments. And if I want to calculate the area of R, I can just calculate the area around the boundary of R of y x dy minus y dx. But the thing is, if you integrate x dy minus y dx along a line segment, it's just given by this difference of x1 with x for the first point and y for the second point, and x for the second point and y for the first point. And so you can just add this up multiple times for each successive pair of points along the shape, and this will give you like straight up formulas for calculating the area of, like, I don't know, 13-sided polygon without doing a lick of trigonometry. You can just add up these symmetric differences like that and get the area. So there's a formula for a polygon with vertices x1, y1 all the way out through xn, yn. You just calculate that, and that gives you the area of the polygon. That's that's pretty cool. That's pretty neat. All right. All right. So next, let's see this one here. I found the area bounded by ellipses. I got an inner ellipse and an outer ellipse. The let's see here. It could be like this. That should have been symmetric. Oh well. But this one is like A, and the inner one, this one is like B. A and B are big, and then the inner ones are I made it too small. C and D. Oh well, sad picture. I'm not sure why I'm doing this. Why am I doing this? There's the inner ellipse, outer ellipse, and all right. So I'm calculating the area. I wanted to calculate the area which is between these two ellipses. All right, and that's relatively easy to do because we just calculated the area, the integral. We just calculated the line integral of x dy minus y dx over an ellipse, right? So we can use that result 2 times here to get the formula for the formula for the area between the inner and the outer ellipse is just pi AB minus pi CD, which of course you could also just deduce from like the usual way we think about areas with holes in them. But okay, anyway, this one's more interesting perhaps. So if you consider the counterclockwise oriented curve with parameterization 10 plus sine of 30t cosine t, and y is 10 plus the sine of 30t sine t. So what's going on here is I'm modulating the radius of a circle essentially. So like the circle maybe is something like this, all right? And that would be radius 10. But what I'm doing is I'm adding sine on both of them. And so the effect of that is it like it makes the radius go basically between 9 and 11. So it's something like this. If you were to graph it, it's like a wiggly circle. All right, and it closes back in on itself again because I made the periodicities match. It's 30. You look at 0 and you got sine of 0. You look at 2 pi, you got sine of 60 pi. So it begins and ends at radius 10, and like I said, it oscillates between radius 9 and radius 11, if you'll allow me that abusive language, because of course it's not a circle, right? It's something else. But the cool thing is, if we look at this, if I wanted to integrate x dy minus y dx over x squared plus y squared over this wiggly circle, if I look at p as minus y over x squared plus y squared and q as x over x squared plus y squared, well, it's not an entirely trivial calculation, but you can show that the partial q partial x and partial p partial y are equal. And so that means I can deform the integral along this crazy wiggly green circle to the integral around something much simpler and easier to calculate, like, oh, I don't know, the unit circle. Not to scale, right? And so because we've got, you know, q partial x q, I can't write, it's too small, partial yp, the that condition is met between the inner counterclockwise oriented orange curve and the outer wiggly green curve. And the deformation theorem says then that the integral around the green curve, which I don't want to calculate, and the integral along the orange curve, which we can calculate pretty easy, as I'll show next, are the same. So the unit circle cosine, and so x dy minus y dx is actually just straight up dt when you calculate it. So we get this is actually x dy minus y dx over, well, x squared plus y squared is 1 on the unit circle, so this vector field is really easy to integrate on the unit circle. It's just dt, actually, and so we get 2 pi for that. And so consequently, the integral of, you know, that same vector field over this much more complicated green curve is also 2 pi. And it really doesn't matter, this particular choice of parameterization. It could literally be anything that, so if you like, you know, here's the unit circle, right? So you take any other curve that just goes once around there, right? Right, and if, as long as it's counterclockwise oriented, if it, because we have the condition qx equal to py in between, you know, in between the inner orange curve and the outer black curve in my current drawing, and because those partial derivatives are equal, the deformation theorem holds, and the integral around the crazy black curve and the integral around the unit circle are the same. That's the deformation theorem. But the integral around the unit circle is just 2 pi. So the integral on the black curve, which I don't even give you a formula for, is also 2 pi. That's a beautiful result. So this is a technique. We should try to make, if we have the case that the curl of the vector field is 0, then we can deform the integral around one loop to another, as long as we pass through a region on which the curl is 0 in that region. And so that's actually the remaining piece in the puzzle, the conservative vector field story. Remember, 1 implies 2 implies 3 implies 4. See, that's how we get, you know, let's see here, 4 implies 1. Suppose U is simply connected. Try to sketch the idea here. Suppose U is simply connected, the curl of f is 0. Let C1 be a closed loop in U, and CR be another loop of radius r inside C1, like so pictured down here. All right. Then since the curl of f is 0, it follows we can apply the deformation theorem, and on the annulus between C1 and CR, and we can get that the integral along C1 of f dot dr is equal to the integral around CR of f dot dr. But of course, since U is simply connected, we can deform CR to a point in this space, right? And the thing is, if you study the way the integral works, as you deform the curve to a point, it makes the integral go to 0, which then by the deformation theorem says that C1 must also be 0. which means we've shown that the curl being 0, remember the curl being 0 is what's needed to apply the deformation theorem. And so what I've shown is then that because we can deform a loop to a point, the integral around a loop is the integral around at a point, which is just 0. And consequently, that gives us that 4 implies 3. And then we also know that 3 implies 2 and 2 implies 1. So that gets us 4 implies 1 in that way. So anyway, that's that. Finally, two-dimensional electrostatics is an interesting thing. I'll let you read about it. I don't think I want to talk about that too much here. But basically, I just show how we can use the divergence form of Green's theorem in the plane to study the electric field lines of a point charge, and we can derive what's called Gauss's law in the plane as saying that the two-dimensional divergence gives me the integral, the double integral of the two-dimensional divergence gives me the flux of the electric field through the normal to that region, which is the two-dimensional analog of Gauss's law. Gauss's law typically is stated with the 3 dimensions in physics, but in fact there is a two-dimensional Gauss's law which we can derive through the arguments which are given here. But anyway, that's not really your course, that's just me blathering on about physics in the middle of Calculus 3, so I'll let you read it. You can take it or leave it, but anyway, I will stop here for now. So thanks.